All right. So we were studying how to solve a matrix and to simplify the data representation, we do convert it into a form of Euclidean. Further, we can reduce it into more like in a form of reduced Euclidean form. Okay. So here you are seeing Euclidean and reduced Euclidean format. I did talk about this thing in yesterday lecture also. Fine. So we are converting in Roeclian or reduced Roeclian format to help reduction method. Okay, fine. So how these things are going, let us check this system of linear equation. Let us suppose you are having this system of linear equation and you have to solve it. Okay. And in order to solve this system of linear equations, solution for whom we are solving it? We are solving it for x, y, and z. You can see there are three variables present, x, y, and z. So we are solving this system of linear equations for this variable. First, convert it into augmented matrix. So this is augmented matrix which you are seeing here. This one, where you are putting the coefficients of these variables x, y, and z coefficients. So these are 2, 1, and -1. Okay, fine. And then the next equation coefficients you are putting, and so on. And then on the right hand side, 8 minus 11 minus 3. This is how we called as an augmented matrix. Okay. And you have to convert this augmented matrix by applying row transformations into Euclidean format. Okay. And for row transformations, whatever be the best possibility, either you can add, either you can subtract, either you can multiply with some scalar value, you are given freedom that you can perform. So this is what been done, that according to the row Euclidean format, we want to convert matrix in such a way that at the lowest row, see, the Euclidean format says there is a rule. Yesterday only we studied. The rule says that all the zeros should come at the bottom. So a row who is having more number of zeros should come at the bottom, and we have to do this thing only, that at least at the these positions we should have zeros. So try to apply such kind of transformations, try to apply row transformation in such a way that your matrix should look in this way. Okay. And we started doing that task, and the operation is L2 plus 3 by 2 L1 is equal to L2. Okay, and L3 plus L1 equal to L3. So how it goes? See, I want to make this 0 and this 0, and I want to make this as 0. So what is the possibility? So if I add these two, row 1 and row 3, and say it as row 3, so obviously this will become 0. Rest of the things are here. And I can also make this as 0 by multiplying row 1 by 3 by 2. Okay, so multiply row 1 by 3 by 2 and add it to row 2. Okay, so this will also become 0 and rest are the terms. Now, now the point is I have to make this as 0. Okay, so why I made these two at 0 initially? Because okay, now the next transformation will be targeted over these two only, so that I can make this as 0. Okay, so here it is. Row 3 minus 4 times of row 2, something like that. Row 3 minus 4 times of row 2. So is equal to row 3. So this will also become 0. Okay, here is the answer. Now check. Is it converted into row echelon format or not? If I can check the result, it's clear that it's a row echelon format only. This one. However, you can further reduce it into in this format. You can still apply the transformations. It's up to you. With row echelon format also, I can get the answers. How? How I can get the answer? See, this represents z. So minus 1 into z equal to, the answer is 1. So z equal to minus 1. I got the value of z. Then this represents y and z. So 1 by 2 into y plus 1 by 2 into z equal to 1. Z I already obtained from above now. So z is minus 1. So y by 2 plus 1 by 2 into minus 1 equal to 1. Okay, and here you can do this thing like y by 2 minus 1 by 2 equal to 1. So this is 3 by 2. So y by 2 is equal to 3 by 2, y equal to 3. And this one represents the x. So finally, we can write 2x plus y minus z equal to 8. Y you know, z you know, you can find the value of x. So to find the values of these variables, we have applied the transformations and we have converted our matrix into row echelon format. And here is furthermore transformations. You can now convert it into reduced echelon format also. So for reduced echelon format, the concept says that in the diagonal, I want all ones and rest all zero. This is what reduced echelon format says. Okay, so what transformation they are planning? So here, here I am having minus 1. I am having minus 1. I can take minus common, so this will be converted into 1. That was not a big deal. Okay, the thing is, let's take care of your row 2 and row 1. Okay, so here is a transformation. Row 2 plus 1 by 2 row 3 is equal to row 2. If I apply this thing, if I apply this thing, here is the answer. This is again, it becomes 0. So your target is to make zeros. Okay, now this thing is again, this thing is 0. Okay, similarly, row 1 minus row 3 is equal to row 1. Okay, row 1 minus row 3. So this is row 3, this is row 1, subtract it. So I got one more term 0 here. You have to follow row transformations only. In my engineering days, when I was also doing this task, now I applied row and column both, because you know, it's a way that you have been taught. Okay, you have been taught to perform row transformation only. So target is visible to you, that what is Cyclian format, what is reduced Cyclian format. Anyhow, with row transformation only, you have to achieve that. Don't try to mix up. Somewhere you applied row, somewhere you applied column. Nah, only row transformation. Okay, so with these transformations, I got this thing. Then still I want to make this as 0. I want this to be as 0. Okay, so what's left here? The transformation is 2L2 equal to L2. That means multiply this row with 2 and you will get, okay. So I got 0 1 0 1 0, and minus of L, that means take the minus sign outside or multiply with the minus with the row 3. So this is also become the same. Now I can subtract. Now I can subtract your row. Okay, row 1. Okay, okay. So row 1 minus row 2 is equal to row 1. So here also I made 0. Here also I made 0. And then I can take 2 common, 1 by 2. That means divide the entire row by 1 by 2. So this is 1 1 1 0 and all these things. Finally, the answers are 2, 3, and minus 1. These are the values of x, y, and z. Either you would have stopped here and solved it, or either you further perform the transformation and just convert them into reduced row Euclidean format. Okay, that's possible. Okay, fine. All right. So, row Euclidean, reduced row Euclidean, we are performing the transformations. These are the system of linear equations. Okay. And we are having different types of solutions. I also told you in previous classes that we can have independent solution, we can have consistent solution, unique solution. That's what we can have. Okay, so so dependent solutions, dependent, that means infinitely many solutions. If I do talk about, then the lines are, I can see that they are, okay, how they are looking: 2x plus 2y equal to 4, 4x plus 4y equal to 8. So they are looking like x plus y equal to 2. So we are having two lines, but they are exactly the same ones. They are actually the same. So here we are having infinitely many solutions. Independent means we are having exactly one solution that we are calling as a unique solution. So these two lines are intersecting, and they are intersecting at a point 2 comma 3. Inconsistent when I don't have any solution for them. Okay, that means they are just like parallel lines. So they are not intersecting. To get a solution, I require intersection of the lines. Then only I can claim that we are having a solution. Else, we don't have any solutions. Okay, fine. So this is the concepts which we have seen previously also. Okay, so I recalled the terms. All right, fine. So we can take like as many as problems, and we can apply this row transformations, convert them into Euclidean, reduce Euclidean. Okay, so I do, let me share the entire screen. Okay, and let's follow up another concepts, but means related to this only. I do have some more topics in this context. Okay, so the property of reduce Euclidean we have seen. Okay, Euclidean format we have seen. The solution we have seen. Pivot element you very well know. Yesterday only I discussed about this thing. Okay, so these are the pivot elements. Fine, we are considering from the left, and first non-zero element is the pivot element. That's it. Fine. And the kind of a solution which I explained just right now, same thing we are doing here. Okay, that means we can perform row transformations anyhow. We can interchange, we can add, we can subtract, we can multiply, whatever possible at your end to perform with the row in order to convert them into reduced format. Okay, Euclidean format, that is all feasible. Okay, so for example, here some elementary row operations are mentioned. Minus r1 plus r2 equal to r2. So here is the result which you are getting over the matrix. Okay, let us suppose this is the augmented matrix. This is the augmented matrix. That means you are having system of linear equations. These are the system of linear equations, and you have converted this system of linear equations into augmented matrix. Okay, and now what you want to do, you have to convert it into Euclidean format. So concept says that converting this into Euclidean format, I want this as 0, this as 0, and this as 0. I need to make these terms 0. Okay, so how I can do that? It's not mandatory that you are following the same approach. It's up to you that what kind of approach you want to make. So they started by making 0 this term. Okay, they started by making 0 this term. Minus r1 plus r2 is r2. Then I want to make this also 0. Minus r1 plus r3 is r3. This is also 0. Okay, one more term I want to make 0. This term. So what I can do is I can multiply row 2. Okay, I can multiply row 2 with 2, and row 3 is equal to row 2 twice of row 2 minus row 3. I can use this technique also. It's also possible. They have used here. So like this one will also become 0. They use one more step, minus row 2 plus row 1 equal to row 1. So this, they made this one also 0. Okay, however, till here, okay, it's not mandatory for me to apply this transformation, make this 0. This one is enough for me, and I can apply the technique. So this is 2. So 2 into z equal to minus 4. So z equal to minus 2. I got the answer. I got the value of z. Similarly, I can say 1 into y plus 3 into z. Y plus 3z is equal to 4. Z I already obtained, minus 2. Put it here. Y into minus 2 into 3 is 6 equal to 4. Y equal to 10. Similarly, I can get the value of x. Or if you still want to solve it ahead, so convert it into reduced Euclidean format. So in reduced Euclidean format, I want all the diagonal to be 1, rest all to be 0. So you can do one thing. 1 by 3 row 3 equal to row 3. So 1 by 2 row 2 equal to row 3. So that's what they have done. And then 2 into row 3 plus row 1. So 2 into row 3. So multiply this row 3 by 2. Add it into row 1. So this term will become 0. Now I'm only available with this 3. What I can do is minus row 3 plus row 2 equal to row 2. So this will also become 0. That's it, done. Here you are getting the final answer. Z is minus 2, y is 10, x is minus 9. And I also got the same thing. Z minus 2, y 10. So either you can stop here or either you can proceed ahead. So the proceeding ahead will give you the final answer. That's it. This is how you do solve. Okay. So one more thing, it came into my mind that I have already explained you about finding the inverse of a matrix. Okay, inverse of a matrix. Okay, this concept is also important. Kindly check the previous lectures. I explained you how to calculate the inverse. I hope you remember the cofactors point. Cofactors. Okay, after determinant only I taught you how to calculate the inverse of a matrix. Singular matrix, non-singular matrix, all these things. So kindly go through those concepts. They are also important. Inverse, transpose. Okay, fine. Now, all right, all right. So here it is now. So the steps of computing to solve three equations, three variable, this matrix of corresponding coefficient in the equation except the last column which contains the constants of the equation is an identity matrix. This is identity, no? This is identity matrix, all one. That means it's an identity. Hence, there is a unique solution of system of equations, and the solution is this thing. So this is identity actually. At the end, na, when you do solve the system of equations and you convert them into reduced row Euclidean format, the end is the identity only, and these are the answers for the identity. Okay, again, okay, again you are having one more system of linear equations. Here you are taking one more component x4. So we are having three equations, four variable. Now what will happen? According to the rule says that you should have you should have as number of equations as the number of variables are present. If you are having four variables, you should have four equations to solve them. But here you are having three equations and four variables. What could be the solution? Okay, what could be the solution? Again, let's approach in a same way. Okay, create an augmented matrix. We did augmented matrix created. Okay, here it is. The idea is same. The idea is to convert this as 0 and this also 0. Okay, so we started with the augmented matrix and apply row transformation. Minus r1 plus r2 is equal to r2. Okay, minus row 1 plus row 2 equal to your row 2. So okay, we made these two as 0. Fine, and then we applied minus row 1 plus row 3 equal to row 3. So we made these also 0. My task is solved here, isn't it? Or not solved? Still, minus 2 and minus 4 are present. Okay, so I can make this thing also 0. So 2 row 2 plus row 3 is equal to row 3. Okay, so this is also 0. So all zeros are present at the last row. Okay, all zeros are present at the last row. Still, we can have a solution like I can perform minus row 2 plus row 1 equal to row 1. So this will become 0. Fine. Furthermore, I can't do anything. These are the as much possible zeros I could have done, and it's over now. No further transformations I can apply. So in this matrix, if you want to solve three equation for variable, we found that we are not getting any identity here. This matrix is not identity. This matrix is not identity. If it would have been identity, then we are going to get a unique solution. But ultimately, we are not getting this thing as identity. बचा ही है नहीं ना कुछ. So here, see, there are two pivot elements corresponding to x1 and x3. They are called as pivot variables. X2 and x4 are free variables. It's saying that x1 and x3 are pivot variables. Why? This is x1, this is x3. These are pivot. X2 and x4, it is saying that they are free variables. Since they are not the pivot elements in the corresponding column, hence the solution to this is given as okay. So yeah, that's what I'm saying now. X1 and x2, these are pivot. These are pivot elements. However, x2 and x4, these terms, x2 and x4, these are free variables. They don't have any specific solution. So x2 and x4 could be any real number, not any specific. They can be any real number. Once a value for them are chosen, values are immediately assigned to x1 and x3. So you choose any value of x2 and x4, and then you can find the value of x1 and x3. This is what you can do. and they are organizing the equation in this way. X1 is equal to, from this, what I can write, x1 plus 2x2 plus 3x4 equal to 2. What I can write from here, x3 minus 2x4 equal to 5. But x4 and x2 I don't know. These are free variables. You can choose any value and you can find value of x1 and x3. That's what they are doing. All right. So by choosing x2 0 and x4 2, the solution will be like, here you can see x1 is minus 4 and x3 is 9. This is how you can perform. Okay, so the solution for three equations, four variable, it requires some considerations. Okay, it requires some considerations. We considered x2 0, x4 2. So according to the choice of these free variables values, you are getting the different solutions. So there could be many solutions. There could be many solutions. We are not denying for a solution. There is a solution, but there are many. So in the first case of your reduced equation, we have seen unique solution. You got the appropriate value of xyz. But in this particular case, when you are having three equations and four variable, so there are many solutions you are obtaining, depending upon the value of x2 or x4 you are choosing. What else? What else? A system of linear equation may have inconsistent solutions also. What is this inconsistent? That means we don't have any unknowns to satisfy all the equations. Now, how it is? Can you give an example? Let us suppose this is your system of equations and this is augmented matrix. Okay, this is augmented matrix. Now again, let's approach make the terms 0. So by seeing here, now I can do minus rho 1 plus rho 2 equal to rho 2. So making this term 0. So you do start from rho 2 and making the term 0 for it. Okay. 1 by 3 rho 2 equal to rho 2. Okay. Take 1 by 3 common from here. So I am getting 0, 1 and minus 1. Then 2 times of rho 1 plus rho 3 is rho 3. 2 times of rho 1 plus rho 3, rho 3. So this is the result for rho 3. Again, this term I made it 0. Also, 4 times of rho 2 plus rho 3 is rho 3. That means I can make this also 0. Fortunately, this also becomes 0. Okay, this also becomes 0. And what next? Rho 2 plus rho 1 equal to rho 1. This also becomes 0. I don't have anything else to do. So by seeing this, what I can say is, this is x1. So from here, x1, y and z are 0. It is looking like 2. Here, not x1, this is x. X, this is looking like 2. This is y and z. Okay, this is y and z. But z, I don't have anything. All are 0. So how can I claim? See, the last row, all are 0. In the last row of the matrix, it is seen that there is inconsistency. 0 is not equal to 15. This is inconsistent. I should have any variable here to claim कि भाई कोई तो equal हो जाओ. I don't have anyone. No variable who can say that I am 15. All are 0. The complete entire row is 0 and here it is 15. तो ये तो हो नहीं सकता, possible नहीं. By seeing this thing only, now we are saying okay, inconsistent. Okay, inconsistent. We are not getting any solution from here. There is inconsistency. So to summarize the facts, what we have learned is, reduce row Euclidean format of the augmented matrix of a linear system. We can conclude the following statements. What are the statements? The linear system of equation has no solution if all are the zero in the last row, but this is not a zero. This is not a zero, rest all are zero. So the system of linear equation, it has no solution. Okay, fine. This is having unique solution. If you are getting identity matrix and everything is present here, unique solution. If here you are not getting identity, but this is zero, this is also zero, you are having, see, there is no unique solution, but there could be infinitely many solutions. All right, got it. That's the point. Okay. So I have taken cases of all the types of equations. Okay, fine. And as far what you have learned by seeing this, yesterday I taught span, I also taught subspace, a very important concept in vectors. And now you have also learned how to solve a system of linear equations. So you should able to understand data in terms of vectors and matrices, because they are having solution. What you have seen right now is matrix, to solve a matrix. So you are available with the data. If you can represent it in a form of vector or in a form of a matrices, you can solve it, else you can't solve. Okay, fine. Because we do perform matrix operations, whether you are dealing with machine learning, whether you are dealing with LLMs, large language models, matrix operations, they are also being performed in LLMs also. We do have weight matrix there, weights, and weights are the values which are assigned to neurons. Okay, so we can't, can't skip this concept of linear algebra, applicable everywhere. Okay, now, so span, you know, subspace, you know, matrix operations, solutions, you know. Okay, and properties of vectors, property of matrices, inverse of a matrix, transpose of a matrix, upper triangular matrix, lower triangular matrix, skew matrix, symmetric matrix, identity matrix, all you know. All right, what else I'm having here to tell you? Okay, what is null space? Null space of a matrix. See, space of a matrix is the set of all vectors which follow this property. Okay, a x vector equal to 0 vector. See, 0 vector comes in a subspace of all the vectors. Okay, ax vector is equal to 0 vector. So what is A here? A is a matrix. A is a matrix. Okay, A is a matrix, and if I multiply it to a vector, this matrix multiplied to a vector, I should get this all 0. Then it's called as a null space. Okay, it's a null space. Now, how you are going to perform this thing? See, this is your matrix, and these are your, it's a vector with all the values x1, x2, x3, x4. So this matrix is of 4 cross 4. This is of 4 cross 1. multiplication is possible. Okay, do it. I got this as a result. And then I can convert it into system of linear equation. This is the result. And then again, just convert it into like augmented matrix and this thing. So this is augmented matrix. Try to solve it like as we do in augment. Try to apply all the row transformations. How many zeros you can make it possible? Just do it. So here last row complete zero. These two are zero. Okay, I got this thing. All right. So here what I am having. This is x1. This is x2. This is x3. This is x4. So at this particular solution, I can say 1 into x1 यानी x1, 2 into x2 2x2, 3 का तो 0 हो गया. ये 3 into x4 3x4 is equal to 0. ये है आपका x3 x3 ये है आपका x4, so 2 is equal to 0. So x3 equal to 2x4. Okay, and x1 is equal to minus 2x2 minus x3x4. I can express here x1. So correspondingly, I can write this into this format. So again, what happened is x2 and x4 are proved to be free variables, and these all the vectors are present in null space, which satisfy the original equation ax equal to 0. That can be represented by linear combination of these two vectors. So these are the vectors, this and this, and x2 and x4 are free. They can achieve any value. They can have any value. I can find x1 and x3 by assuming any value of x3 and x4. That's what I can do. So the linear combination of two vectors in a span is the span of two vectors, and it is true to say that null space A is null space minus space A equal to span. Now, what does this mean? What this mean? You got to know about null space or not. You are having a matrix, you applied it with x, you got 0. 0 vector. 0 vector is a vector which is present in each and every subspace. Okay, 0 is present in each and every subspace, 0 vector. But this property is null space. Okay, this is null space. So we took one matrix, we applied all these things, we did solve it, and the solution says that okay, you got these things like okay, free variables x2 and x4 you got. Okay, these are the free variables x2 and x4. And we are having these free variables, and we are having x1 x3 also, which are dependent on these variables. So it said that all the vectors are present in null space, and they are satisfying this equation ax equal to 0. So we can represent them in a linear combination of two vectors. Okay, this is one vector, this is one vector. So by the linear combination of these two vectors, I can represent them. Okay, and at the end, what it is saying that null space of A is equal to span of these two, which I obtained. Okay, null space is equal to span of these two vectors, which I obtained here. These two. Why? Why? Can't you achieve this thing? See what you got, minus 2100. From where you got this thing, minus 2100? How? Yes, from where you got this thing? Minus 2 1 0 0 minus 3 0 2 1. See, x4, this is x2. So in x2 I am having minus 2. Okay, I am having minus 2. What else? Where I got this 1? Do you have anything related to this one, so that I can have multiply with x2? Instead I am having x4, that is having minus 3. So minus 3 is there. And 2x4 also. So minus 3x4, 2x4. One more x4 I am having in multiplication. So how I got all these things? Can you clear the terms? Can you clear it? Yes. These were the final equations. If I refer to the matrix. Okay, these are the final equations if I refer to the matrix. Okay, so x1 and x3 are coming in terms of x2 and x4. Fine. They are coming in terms of x2 and x4. So x2 and x4, these are the free variables. All right. I can choose anything and I can get the value of x1 and x3 from here, because x1 and x3 are dependent on them. And this is one of the solution which they are claiming here, that this entire vector is dependent upon x2 and x4. And this is one of the these are two are the vectors which are forming a span. They are forming a span in which I can get a null space. These two are the span, these two vectors. And span means I can create, if with the help of these two vectors I can create. That means with the help of this, can I get another vector or not? So this is the span. Okay. So correspondingly it is writing. It might have assumed any value of x2. I can take x2 as 1, x4 as 1. I can take and I can find the value of x1, and I can find the value of x3. I can get any other vector. So the point is clear that these two are free variables. Okay, free variables. I can assume anything with that. Only the concept says your property should be following. So null space should satisfy this thing, and that's what we are writing here. Okay, null space A is equal to span of these two vectors. Okay, this vector and this vector. This is one of the solution which they are getting. You can have any other also. Okay, because once you are having free vectors, you can put any value. You can find any value of x1 and x3. Just we have seen above. You can have many solutions. So null space शो लीनियरली इंडिपेंडेंस, जब से ये तो बोल रहा हूं भाई आपको, इंडिपेंडेंस लीनियरली इंडिपेंडेंस में तो था मेनी सॉल्यूशंस of the column vectors. So if the column vectors are independent, the null space of that matrix is going to be consistent of the zero vector. The null space of a matrix contains zero vector. It means that the columns of that matrix are linearly independent. So what you have seen above, one case was there, na, independence. Yes, you have performed the solution of independence. Okay, yeah, here see, free variables. Once you got the free variables, okay, what was the point we mentioned? What was the point mentioned for the free variables? Here it is the free variable. And because you are getting the free variable, okay, here You are getting many solutions for it. Okay. The different choices of free variable can give you different solutions. Same thing here is also happening. Okay, so I took 0 as an answer. That means um, here 0. We took 0. Okay, this one is 0 in the augmented matrix, and we are getting independent solutions. That's what Ax equal to 0 says. Ax equal to 0. We are having independent solutions. That's a null space. All right. And then what you are having next? Okay, what you are having next? Okay, so okay, let me clear this thing so we can read the lines. Huh. If the column vectors of a matrix are linearly independent, column vectors are independent, then the null space of the matrix is going to be consist of the zero vector. It is having a zero vector. Independent है तो zero vector होगा. Okay, and if the null space of a matrix only contains zero vector, यदि only है, only contain, this means that the columns of that matrix are linearly independent. To better understand this, let's do little maths. If you are having a matrix A n cross m, A n cross m means n is the number of rows, m is the number of columns. If you are having this thing, so we can rewrite it in this format: a vector, a1 vector, a2 vector, an vector. So to calculate the null space of A, you can follow this thing: ax equal to 0. That's what they have written. So this is your matrix, this is your vector, and this is your okay, x1 a1, x2 a2, and so on. Okay, you do multiply ना, you do multiply with them. भाई ये एक वेक्टर है, this is a vector, this is also a vector. अरे understand ना? See, if I do write like this: 1 2 3 4 5 6 7 8 9. So 1 2 3 is a vector. 1 2 3 is a vector. Let us suppose a1. 4 5 6 is a vector. Let us suppose a2. 7 8 9 is a vector. Let us suppose a3. And that's what it is saying: a1 a2 a3. तो x1 into a1, x2 into a2, and so on, वो multiply कर रहा है. So with this, I am multiplying x1. With this, I am multiplying x2. With this, I am multiplying x3, and so on. वो कर रहा है. So the vectors are linearly independent if only solution of the linear combination is this or as zero. So यदि सारे के सारे zero हो जाएंगे तो उसको independent मिल जाएगा. So linearly independent हो जाएंगे वो. If all these comes to be like, यदि ये span का value zero हो जाएगा तो linearly independent हो जाएगा. Okay, बस यही मैथ्स है उसकी. So उसके लिए ये कह रहा है कि this should have to be zero. Okay, because according to the span, what we wrote is the vectors are c1 v1, c2 v2, c3 v3. Means this is the if v1 v2 v3 are span, so this is what is followed. So if you want to make them linearly independent, तो भाई उसके लिए c1 c2 c3 सब जीरो होना चाहिए, तभी जाके जीरो वेक्टर होगा ये. That's it. Then only it will be linearly independent. So this is null space. So just remember, for the null space, ax equal to 0. For the null space, that's what you have to remember: ax equal to 0. That is, multiply a matrix with a vector, it should be a 0 vector. This defines a null space. And in case of null space, you are having linearly independent solution. Don't stress too much. Okay, we are having column space also. What is this column space? Column space of a matrix is a span that is created by column vectors. Okay. In other words, based upon the definition span, column space of a matrix is all the vectors that are represented by linear combination of the columns. Okay. How it's going to be? Do you have any solution? Okay. Do you have any solution for the column space? They are taking one example. Okay, that means consider a matrix. that we calculated its null space in the previous section. So this is a matrix. Okay. And okay, they are solving it to, okay, this is the final solution which we obtained in the above. Okay, after doing the augmentation, after performing the row transformation, this was the result which we got over this. Okay, after performing the augmentation and all the row transformation, we got this result. And what they are doing, this we know, ये दोनों span है, ये दोनों span है. Okay, another concept they are telling. So I think for column, we should go through these points. Column space. So the important points to understand the column space is, column space of a matrix is a valid subspace. If you want to solve the equation Ax equal to B, but vector B is not in the column space A, it could be concluded that Ax equal to B has no solution. Means, again it is referring Ax equal to B, B is not 0. It is not 0. And and vector B is also not in the column space A, means it is also not present in one of the columns of the matrix. Then it is a, then this equation has no solution. So if it is 0, all zeros, if Ax equal to B, sorry, if Ax equal to 0, then it's independently solutions, independent solutions. If Ax equal to B, and if B is not present in the column space, like this is the column space, Ca equal to span of the column vectors. That means you are going to find the span, and if this vector B is present in the span, then it is fine. If it is not present, then no solution. Then there is no solution. But if in the equation at least one solution, it's true that the vector B is definitely a member of column space. That means if you are having a span of this and the B, which is one of the vector, if it is present in the span, then you are having one solution. So still it is focusing upon infinitely solution, no solution, one solution, or unique solution. And it is targeting the span and the spaces. So what it told you so far, what it told that, okay, Ax equal to 0. A is a matrix. X is a vector. Okay. And you solved this thing. You got independent values. Independent values. You got it. It told that here the independence x2, x4, which you have seen, we are having a span, we are having two vectors there. These two vectors define the span. If you are having Ax equal to B and B is not 0, now again you will solve it. B is not 0, again you will solve it. You will perform the augmentation, you will perform the row transformations, everything you do, you solve it. And with this, you will again make a span. That means the vectors you will make. If this B is present in the span, if it is present, then there exists a solution, unique solution. But if B is not present in the span, then there is no solution. Okay, ये बता रहा है वो. This is what it is telling. Okay, fine. So yeah, these are the things. What is nullity? What is nullity of a matrix? What is nullity of a matrix? Dimension of the null space. That is called as a nullity. That means the nullity of any matrix is equal to the number of non-pivot columns, free variables in the reduced Euclidean format. As many as number of free variables you are having, that is called as a nullity of a matrix. Remember this. As many as free variables you are having, that is the nullity of a vector, of a matrix. Rank I already explained you. Rank we have already done. I explained you what is rank. Okay. So as many as free variables you are having, that defines nullity. Rank means rank of a matrix means number of independent variables you are having. That is the rank. We have seen number of independent, like uh, if you wrote this thing 1 2 3 4 2 4 6 10. So this matrix is having rank 2. Why? Because I can't write this in terms of this. If I can't do that, so rank 2. So it's giving one property, rank plus nullity equal to number of columns. Nullity means number of free variables, rank is obviously. So maybe you are getting some free variables, so rank is 2 and nullity is also 2 for this thing. So the total number of columns here is 4. Okay, fine. So these are the core concepts of matrices, vectors, and related to linear algebra. All right. I hope there are some terms which are still, because it's not been easy to capture the concepts in a one go itself. So span and subspaces. Okay, subspace. These are important, and corresponding to that only, then the rest of the concept which I told today it went. Okay, that is the zero subspace, null subspace. Okay, and rest of the things. However, solution Euclidean form, reduced Euclidean form, that you have done, and you all the different examples I have taught you. So now you are confident with solving the system of linear equations. Okay, so here we are going to use these operations ahead in the algorithms. Okay, so there you will feel comfortable because you are having the knowledge of the eigenvalue, eigenvectors. Okay, and this matrix operations, now you are aware of these things. Fine. So we have learned a lot. That means we have gone through the major portion of linear algebra in terms of matrices and the vectors. Okay, so let me stop sharing.